Greetings. This is Rishik Ganta of registration number 19BCE1494, recording this video for the digital assignment 3 of CSE1006. The topic that I got today is Fermat and Euler's theorems. Coming to the topic, these are the contents that are going to be discussed today. Uh, First, I'm going to discuss prime numbers, under which prime factorization, relatively prime numbers, and greatest common divisor is going to be discussed. And after that, Fermat's theorem is going to be discussed, in which Fermat theorem proof is going to be given. After that, Euler quotient function, Euler's theorem, and its applications are going to be discussed. And in the end, a summary is going to be given. Prime numbers. So coming to prime numbers, a prime number can be defined as a number which is divisible only by 1 and itself. It has no other factors. For example, 2, 3, 5, 7, 11, 13, 17 and so on are examples of prime numbers. 1 can also be considered as a prime number, but it is usually not very useful. Prime factorization. To factorize a number means to write it as a product of its factors. So n can, for example, a number n can be written as a product of its factors a, b and c. In the example, we can see 100 can be written as a product of 5 into 5 into 2 into 2, that is 5 square into 2 square. Prime factorization of a number n is written as its product of prime numbers. For example, for the number 143, it can be written as 11 into 13, both of which are prime numbers and are factors of 143. Relatively prime numbers. Two numbers are said to be relatively prime if they have no common divisors other than 1. That is, for example, 10 and 21 are relatively prime in respect to each other, as 10, which has factors of 1, 2, 5 and 10, and 21 has factors of 1, 3, 7 and 21. We can see that they have no common factors except for 1. The greatest common divisor, GCD, of two relatively prime numbers can be determined by comparing their prime factorizations and selecting the least powers. A greatest common divisor. We can explain this using an example. In the example, consider 125, which can be written as 5 power 3, and 200, which can be written as a product of 2 power 3 into 5 power 2, 5 to the power 2. That is, when we consider the greatest common divisor of 125 and 200, we can see that there are no other common factors other than 5 to the power 2. So the GCD can be written as 2 power 0 into 5 power 2, that is 25. If the two numbers are relatively prime, then their GCD will always be 1. Consider the example of 10 and 21. 10 has factors 1, 2, 5 and 10, and 21 has factors 1, 3, 7 and 21. Thus, their GCD is going to be 1, as 1 is the only common factor for them. So, it then follows that a prime number is also relatively prime to any other number other than itself and 1. That means, consider a prime number 7 and any other number like 8. So the factors of 7 is going to be 1 and 7, and the factors of 8 is going to be 1, 2 and 4 and 8 itself. So we can see that the only common factor for 7 and 8 is 1, and thus 7 and 8 are said to be relatively prime. Now coming to Fermat's theorem. Fermat theorem states that if our number p is prime and a is an integer that is not divisible by p, then a raised to the power p minus 1 is concurrent to 1 mod p. And for every integer a to the power p is concurrent to a mod p. This theorem is also known as Fermat's little theorem. It is used in public key, that is public key RSA and primality testing. Fermat's theorem's proof. So consider a set of positive integers less than p such that the set consists 1, 2, 3, so on until p minus 1, and multiply each number by a and modulo p to get the set x, which contains a mod p, 2 mod 2a mod p, so on until p minus 1 a mod p. No elements of x is 0 and equal since p does not divide a. Multiplying the numbers in both sets, that is set p and set x, we can get the, and taking the result modulus p yields Fermat's theorem yields a into 2a into so on until p minus 1a, and that is concurrent to 1 into 2 into so on until p minus 1 mod p. So on simplifying that, we get a raised to the power p minus 1 into p minus 1 factorial, which is also concurrent to p minus 1 factorial mod p. Thus, on equating p minus 1 factorial term from both the sides, it is relatively prime to p, and the result becomes a to the power p minus 1 is concurrent to 1 mod p. An alternative form of Fermat's theorem is given as a to the power p is concurrent to a mod p. Euler-Torsion function phi of n. Phi of n gives us the function phi of n, which is called Euler-Torsion function, gives us how many numbers are there how many numbers there are between 1 and minus 1, 1 and n minus 1, such that they are relatively prime to n. For example, if we take phi of 4, then we get the answer as 2, because between 1 and 3, the numbers 1 and between 1 and 3, the numbers 1 and 3 are relatively prime to 4. And for phi of 5, we get the answer as 4, as 1, 2, 3, and 4 are relatively prime to 5. And again, when we take phi of 6, when we take psi of 6, we get 2, which is 1 comma 5, which are relatively prime to 6. And if we take phi of 7, we get 6. We get the answer as 6, as 1, 2, 3, 4, 5, and 6 are relatively prime to 7. Therefore, from phi of 5 and phi of 7, we can say that phi of n will always be n minus 1 whenever n is a prime number. This implies that psi of n will be easy to calculate when n has exactly two different prime factors. Psi of p into q is equal to p minus 1 into q minus 1 if p and q are prime. If the GCD, which is explained before, GCD of a comma p is 1 and a is less than p, then a raised to the power psi of p is concurrent to 1 mod p. In other words, if a and p are relatively prime and a being the smaller integer, then we multiply a with itself phi of p times and divide the result by p, and the remainder will be 1. Euler's theorem. Statement of Euler's theorem. For every a and n that are relatively prime, then a psi of a to the power psi of n is concurrent to 1 mod n. The above equation is true if n is prime, because psi of n is equal to n minus 1, which we have seen before, and Fermat's theorem also holds. Consider the set of integers labeled as R set of x1, x2, x3, so on, x psi of n. Here each element x of I of R is a unique positive integer less than n with a GCD of xi comma n equal to 1. That is, all of R is a set of relatively prime numbers to n. Multiply each element by a and modulo n. Then we get the set S equal to a x1 mod n, a x2 mod n, so on until a x psi of n mod n. S, the set S is a permutation of R because the set S can be called as a permutation of R because a and xi is relatively prime to n. So a into axi must also be relatively prime to n. Thus, the elements of S are integers that are less than n and that are relatively prime to n. There are no duplicates in S. If axi mod n equal to axi mod n, then x of I, if axi mod n equal to axj mod n, then xi equal to xj. The multiplication of axi mod n from I equal to 1 to psi of n is equal to the multiplication of xi from I equal to 1 to psi of n. That equal to multiplication of axi from I equal to 1 to psi of n, that and that equal to multiplication of xi mod n from I equal to 1 to psi of n. This again further results to a psi of n into xi, multiplication of xi from I equal to 1 to psi of n, which is also concurrent to multiplication of xi mod n from I equal to 1 to psi of n. Equating multiplication of xi from I equal to 1 to psi of n on both sides, we get a psi of n is concurrent to 1 mod n, and thus the Euler's theorem is proved. Applications. Both Fermat's and Euler's theorem plays an important role in public key cryptography. It is also used in periodic decimal expansion. An example. Examples of application. Choose two large prime numbers p and q. Let p and q be p equal to 7 and q equal to 17. Now calculate n equal to p into q. Thus n equal to 7 into 17, which is 119. Now select the public key, that is the encryption key E, such that it is not a factor of p of I into p minus 1. It is not a factor of p minus 1 into q minus 1. Now p minus 1 here is 7 minus 1 and q minus 1 here is 17 minus 1. So that equal to 6 into 16, which is 96. Factors of 96 are 2 and 3 because 96 can be written as 2 to the power 5 into 3. So E has to be a prime to 96. So let E equal to 5. Now select the private key, that is a decryption key D, such that the following equation is true. D into E mod P minus 1 into Q minus 1 equal to 1. Substitute the values of E, P and Q in the equation. Let us choose D equal to 77, since 5 into 77 mod 96 is equal to 385 mod 96, which is equal to 1, which satisfies the above condition. For the encryption, calculate the ciphertext CT from the plain text as shown in the following equation. This is the equation: CT equal to PT to the power E mod n. Let us consider an encoding of alphabets such as A equal to 1, B equal to 2, C equal to 3, so on until Z equal to 26. We have to encrypt a single alphabet F f equal to 6 using this scheme with B's public key as 77, which is known to A and B, and B's private key as 5, which is only known to B. Now the equation, the ciphertext is generated as Ct equal to P to the Pt to the power E mod 119, that is equal to 65 to the power 5 mod 119, which is 41. Send Ct as a ciphertext to the receiver. For the decryption at the receiver, calculate the plain text Pt from the ciphertext Ct as follows: Pt equal to Ct power d mod n. Pt equal to Ct power d mod n, that is equal to 119 equal to 41 to the power 77 mod 119, which is equal to 6, which is the original plain text, that is the code of F. Thus, it is decrypted successfully. This is the example. This is the encryption algorithm using the public key, and this is the decryption algorithm using the private key. In the encryption algorithm, encode the original character using a equal to 1, b equal to 2, etc. Raise a number to the power of e, here 5. Divide the result by 119 and get the remainder. The resulting number is the ciphertext. And in the decryption algorithm, raise the number to the power of t, here 77. Divide the result by 119 and get the remainder. The resulting number is the plain text. Decode the original character using a equal to 1, 1 equal to a, 2 equal to b, and so on. Here we can see a flow chart where f is taken. F is encoded as 6. 6 is raised to the power 5, which results in a modulo of 119. I'm sorry, 6 to the power 5 modulo 119 results in 41. 41 is sent as the encrypted message. Now 41 is raised to the power 77 into modulo 119, which gives 6. And 6 is the key for F. And F is the decrypted message. So in summary, we can say that today I have covered firstly the prime numbers, prime factorization, and greatest common divisor. After that, the Fermat's theorem and its proof is done. And after Fermat's theorem, Euler-Torsion function is discussed. Then lastly, Euler's theorem is discussed, and an example for both of these are given. Thank you.